we are going to finish the proof of Pansu's version of the Rademacher theorem. We will prove that for every Lipschitz map between Carnot groups, there is a full measure set on which the intrinsic differential exists, and it is a group homomorphism. We already proved this theorem in the case of curves, namely when the domain is the real line or an interval. And today we will conclude. Okay, let's recall the setting of our theorem. So we have a map, let's call it F, from G to H, a Lipschitz map, a Lipschitz map between Carnot groups. And the state means that there exists a full measure set, a set E inside G of full measure, such that at almost every point the intrinsic differential exists, such that at every point of E, the intrinsic differential of F exists and is a group homomorphism. The differential exists if means that, I recall you that this means, so let's call it, at every point, let's call it P. Then if we take the function, construct as follow: you dilate by some epsilon, and then you left translate by P, you apply F, and then you translate back by Fp minus 1, and then you dilate again, then this has to converge uniformly on compact set to what we have denoted as dp of F. Okay, so we already proved the case of curves. So we already proved that Lipschitz curves gamma from an interval or the real line to G into a Carnot group G are intrinsically differentiable. Differentiable almost everywhere. Next, so for the general setting, now we will need two facts from measure theory. So for general setting, we need two facts from measure theory. Okay, so the first one is Aggro Theorem. So Aggro Theorem for metric spaces. So the theorem says that suppose you have a measure space, and with a finite measure, and suppose you have a separable metric space, and suppose you have a sequence of, or like a family of maps, depending on a parameter, maps from X to Y, measurable, with T a parameter, T in 0 infinity. And suppose that these maps are converging to some other measurable map as t go to infinity, and this convergence is almost everywhere. Then the Aggro theorem says that for all error eta, there exists a set K in X, a measurable set, which has almost all measure. So because X minus K has measure less than eta. And now the convergence of the maps restricted to K is uniform. Okay. This is the first fact that I want to recall without proof. I think you should know this from some course on measure theory. The second fact is about points of density. Now, whenever you have a metric space with some assumption very weak, for example, doubling metric space, then it is true that whenever you take a measurable set, then almost every point is a density point of this set. Right? So as soon as you have a theory of Lebesgue differentiation, you have such result. Maybe I will state it just for Carnot groups, because it's a little bit easier to state and you have slightly stronger conclusion. So I just invite you to solve this as an exercise. So points of density 1 in Carnot groups. Okay, suppose G is a Carnot group. We have mu, some fixed hard measure, and we consider a Borel subset. Then there exists a set, let's denote it with E circle, the subset of E, such that the measure of E minus E0 is 0, so it's almost all. And now what we have is that for all points P in E0, when you dilate the set, so let's translate it first to the origin, and you translate then let's look at the intersection with the unit ball. So maybe close. Translate intersect with the unit ball, and you compare this with the unit ball. So let's take measures. So this ratio goes to 1 as lambda goes to infinity. So what it says that a point P, when you zoom around the point P, the more you zoom, the more you see the set E. Of course, here we can put either E naught or E because they have the same measure. Okay. All right. So, and as a consequence, this is what we are going to use actually in the proof, is that whenever you have a point of density and you take an element of the group which you think as a direction, right? Then, and what you have to think now is then what you would like to take is the point P delta epsilon V, right? So you want to approximate this point, but this point might not be in E0. No? Then what it says is that the consequence is then there exists points Q epsilon in E0 such that now they behave in a similar way in direction. So when you dilate, put 1 over epsilon translate p minus 1 q epsilon, this converge to v as epsilon goes to 0. Okay. And the way you do it, you just take this point and then you just project it on E0. Since E0 is as a density point, you're going to have this property. Okay? I leave this to this fact as an exercise, and now we conclude the proof. Okay. So here's the proof of Pansu's version of Rademacher theorem. So let's give the name of the map. So we say we have a Lipschitz map. Let's say that the constant is L. So we have a L Lipschitz map between Carnot. Let's denote f as f p epsilon variable x. These are the difference quotients. So you dilate by 1 over epsilon. You translate, so fp minus 1, f of p delta epsilon x. Okay, so let's define this. Okay, let's remember some things we already said. So first of all, by Ascoliar's law, for all sequences ej going to 0, there exist subsequences such that these ratios, these difference quotients, converge to something. They converge uniformly on compact sets. So this statement is true for all p. Okay, but a priori this limit might not be unique and might not be a group homomorphism. 2, okay. Remember the fact that we already proved the version for the for curves. So what it means? It means that if I fix an element in the first layer of the group, then I can look at the curve that for p real associate the curve exp tx, right? Because x is a vector in v1, this curve has finite length. So actually this curve is Lipschitz. Then I can also translate, and this is also a Lipschitz curve. Since I can compose Lipschitz maps, this map here is a Lipschitz map, and therefore is differentiable almost everywhere on R. Okay, so this map here is differentiable almost everywhere. Okay, so let's use this differentiability, letting x vary among elements of a basis of V1. So fix x1, xm, say, a basis of V1. And let's give a name to the one parameter subgroups. So Ri is exp, the image of the one parameter subgroups. Okay. Now, so if you fix I, then remember, so you have Ri, and then you have all the cosets, right? You have all the cosets that Ri defines. In exponential coordinates, these are lines, and you can take a transverse half space, right? And now what you know is that on each line, you will be able to apply the one-dimensional version of Pansu's Rademacher theorem, have differentiability almost everywhere. And now what you have, so is you have a set that also on each line you have a full measure set. By Fubini, then you have a full measure set of the space. So you apply Fubini. What does Fubini tells us? Tells us that there exists a set in G, full measure set, such that for all points in E and for all I from 1 to M, then if we consider the map P epsilon M, remember, so P epsilon, right? So we are translating with P and we are dilating by epsilon, okay? This map here, so P, think that is fixed, restricted to Ri. This map converges to some map. Let's call it Fi tilde P0. So the first maps, just let's call it F tilde I P epsilon. This map converge uniformly on compact sets. Okay, so we have convergence of these maps. Now we look at the following map. So for all P in the set E, we can associate this map F. So think that I is fixed for the moment, P epsilon, okay? This is a map, is a Lipschitz map, so with constant L. So let's denote, this is the space of L Lipschitz maps from Ri value into H. Okay. So this object here, one can easily find the distance that metrizes it. So, right? And this map here becomes a measurable map. We know that is converging. Now, saying that this map converges is the same as saying that you have convergence of these maps uniformly on compact sets. Now, what we are going to do, we are going to apply Aggro to these maps. Okay, what does Aggro tells us? That for all delta and R, there exists E delta R, because okay, E is does not have finite measure, so we have to intersect with the ball at the origin of radius R. So let's call it just BR. Right? So this is the ball of radius R, such that so the measure is almost everything. No, not BR, but E minus E delta R is almost everything. It's less than delta. And if so, now the convergence is uniform on this set here. The convergence is uniformly, and therefore this means that if we take P epsilon, a sequence or a family of points in E delta R, for which P epsilon converges to P in E delta R, then this map F tilde J P epsilon is converged. So let me first here put just P. Right? So we know that we have this convergence, right? Uniformly on compact sets. But now we know that the convergence is uniform in the space, in this space here, and therefore here I can put a point that varies. Okay, so uniformly on compact sets. Okay, this is how we are going to use Aggro. And let's take points of density. Take E0, E0 delta R, the density point or namely the points of density 1 of M delta R. So for now, so delta and R are fixed. Okay, at the end, we will just take the union of all these sets. Okay. Now, one first thing to notice is that for all V in the group G, there is always a point. So because we have points of density, I think we already said this at the beginning of the video, that you can take a sequence in the set if Q. So okay, we have to fix Q. Okay, if Q. So for all Q in E0, for all G in G, there exists points for which this converges to V. Again, you should think of Q epsilon almost equal to P delta epsilon V. But we have to project it on E0. And now we define this following set. It's going to be important. dP is the set of all directions, like all elements in G, for which for all sequence Q epsilon in E0, such that delta 1 over epsilon P minus 1 Q epsilon converges to V, if we know that there is one, then we have there exists the limit of delta 1 over epsilon of Fp minus 1 Fq epsilon. Okay. Now, you see, if you could take here to be P delta epsilon V, then what we are exactly assuming is that the directional derivative in V exists. But now we are asking something even stronger in some sense, because we are not asking for this sequence, but for all those sequences that are, so that if this is Q epsilon, that also converge converge to Q and converge in direction to V. Of course, that we only ask for those that stay in E0. So let's call this map Fp0V, just by definition. Let's define it like this. So this limit exists, and because it exists for all sequence, then it's independent of the sequence. Therefore, we have a map Fp0 that goes from dP to H. Now, what I want to make you realize that if we have the dP is all of G, then it means that we really have a differential. We really have the map, the dilation of the maps converge to something, because you see, this is independent on the sequence, right? So this means that if we have that Fp epsilon m, if epsilon m is a sequence for which this sequence of maps converge, if this sequence converges, then it does converge to Fp0, at least on dP, okay? On dP. So, and remember that up to subsequences, we always have convergence of these maps. We have to prove that the sequence, the blobs all converge to the same, so they are the same. Okay. All right, so here's the first claim, important claim. So let's call it claim 1 about this set. So fix V in Rj, so fix J, fix V in Rj, fix Q epsilon and P epsilon in E0 with P epsilon converging to P. Remember, P is fixed, and the dilation 1 over epsilon P minus 1 epsilon Q converge to V. So assume we have this property here. You see? Yeah. Okay. If you have a sequence like this, then delta 1 over epsilon F P epsilon minus 1 F Q epsilon, this converges to the same things, Fj P0 V. Did we put the index? Okay. Right. So let's go. This is tilde. Okay, I put a tilde here. Right. So this map here is the map that we defined before as these restrictions. So these are the maps that we have because of the direction, the derivative along Ri. Okay, J. Okay, so what I'm saying now, if V is in Rj, not only Fp0 coincide with the F tilde, but also instead of, this is what we had in here. But here you also can put a P that varies. P here can also varies as long as converges to P, right? So for directions that are in Dj, this is an improvement. So this in particular will tell you that all the directions are J that are in this domain dP. Okay, so let's prove this claim. Okay, so let's check that the distance between these two values goes to 0. Okay, so I have to write it. So distance between delta 1 over epsilon of F P epsilon minus 1 times F Q epsilon, comma F tilde P0 J V. Okay. Now, let's, so this map here, we can see it as the map F centered at P epsilon dilated by Tj. So here really, this is an equality actually. This is the distance between, so I can take the map is the map center of Fp epsilon dilated by epsilon of the point, okay, do the calculation correctly, the point is 1 over epsilon. Remember, I can, this is a homomorphism, so it's the dilation of this times the dilation of this. So it's delta epsilon of P epsilon minus 1 Q epsilon. Okay. Right. So this is the first map, and the second one just write the same. Tilde J P0 V. Okay. Now I use the triangle inequality. Okay. So I just copy the map. Okay. Copy. And now I put the triangle inequality. Put one more point. So the point that I put is F P epsilon V plus distance F P epsilon V. Okay. Now the first term, see, is these are 2 points on which I apply a map that is L Lipschitz. So this is less or equal than the Lipschitz constant times the distance between delta 1 over epsilon P epsilon minus 1 Q epsilon and V. And because of this assumption here, then we have that this distance goes to 0. Instead, here, then since P is in the in the point on which we have Aggro, because of Aggro we have uniform convergence, then as epsilon goes to 0, since epsilon goes to P and the convergence is uniform, also this limit, this distance goes to 0. This one goes to 0 because of uniform convergence. And this is the proof of this first claim. Okay, next claim. Let's call it claim 2. If we have a direction in dp and we have another direction in rj, then I claim that w times v is also in the domain dp. Actually, something more precise is that the function fp0 on the value w times v is equal to fp0 of w, which is defined because w is in dp, times f p0 tilde j v. Okay, this is my claim. So proof. Okay, to prove it, so we have to take a sequence for this value wv. So we take q epsilon in E0 such that delta 1 over epsilon of p minus 1 q epsilon converges to wv. Now that we have this q epsilon, and we have that q is a point of density, we can take p epsilon in E0 such that delta 1 over epsilon p epsilon minus 1 q epsilon is converge in direction to v. Then what happens if we take 1 over epsilon of f p minus 1 f q epsilon, right? Which is the sequence that we have to consider and take the limit to define this number here. So what is this? So this is, okay, let's apply that we have, so delta 1 over epsilon is a groupomorphism, f p minus 1, and here put f q epsilon. But now I multiply and divide by f p epsilon, delta 1 over epsilon, f p epsilon minus 1. Yeah. Now, the first limit, this converges to fp0w because of the definition of let me think for a moment. Yeah. So one should observe that from these two properties, then we have that delta 1 over epsilon p minus 1 p epsilon, this converge to w. And therefore, w is in dp. Since w is in dp, this is a we can take this as a the p epsilon as a sequence, and we have that this is the limit. Okay, so this is because v is in w is in dp, and instead here this one converges to f tilde j p0 of v because of the previous claim, because of this claim. This is exactly what we have. So this is because of claim 1. And also this claim is proved. Okay. Now, let's put things together. We're almost done. So what are the conclusion consequences? So, first of all, okay, maybe this is something that one should have realized before, that the identity of the group is in this domain. Okay, this is right. So what I'm saying is that if I have a sequence p minus 1 q epsilon that converges to the identity of the group, right? Then just by Lipschitz property, we have that one can show that f p minus 1 f q epsilon is easy to prove that this converges to the identity. Okay, now this is identity in H. This was identity in G. So in particular, we have convergence. So one is in DP. Okay. Now, this second claim implies that. So first of all, we have that R1 and Rm are subset of DP, right? Because one is in DP, V is in Rj, so V is in DP. So all of them are in DP. And again, because of this fact, we can take all the products. But for some n big enough, G, the whole group, can be written as the product of all the possible n products of elements in these one parameter subgroups. Okay, for n big enough, this is it's also in DP. So this and this is for n big enough, for n big, finite. Okay, so this means that DP contains all of G. Okay, then what is it that we are saying? We are saying that at P now is at this E0 was a E0 of delta R. What we have is that there exists partial derivative at every direction, and moreover, every value of this partial derivative, every blow up coincide with the map we define. What was the name? With this fp0. So this map of partial derivatives. And therefore, what we have is that all blow-ups are the same. All the possible subsequence of dilations coincide. Okay, and therefore the blow-up exists as a limit of uniform on compact sets. So what we have is that the intrinsic derivative exists, the intrinsic differential exists. Now, what we have to just conclude is that this differential is a group homomorphism. Okay, again from this claim, from claim 2. So if you have points, so let's say we have G that is of the form, let's call it G1 times G1 times Gn, say, and G prime is G1 prime times Gn prime for n large enough, and all Gi and Gi prime are in some R, or say the union are M. Then what we can what we can write because of this claim is that this intrinsic differential at f in the direction of G, right? So what we said that this is the same of saying this map f0 fp0 G we don't want just G, we want the product G times G prime, so fp 0, so we have G1 times Gn G1 prime times Gn prime. Now claim 2 iterated gives us this fp0 G1 fp0 Gn times fp0 G1 prime fp0 Gn prime. And now again we can put them together. Again, applying the claim 2. Again, this is fp0 G fp0 G prime, which is then the differential of f in the direction of G, differential of f at G prime. So what we have proved is that the map dpf, which exists at P, is a group homomorphism. Okay, and this was for all P in E0 R delta R. Remember, these are not full measure sets, but have measure on almost full measure in the ball of radius R, then have measure almost everything except an error of epsilon. And therefore, we get intrinsic differentiability on all points of the set union over delta greater than 0 and R greater than 0 of E0 delta R, which has full measure. And this concludes the proof of Pansu's theorem. If you liked the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel, clicking below.